7.3, using the constant e, which is approximately equal to 2.718 dot dot dot. It's a non-terminating, non-repeating number. What is that type of number when something goes on and forever and doesn't? Very good. Irrational number. This is an irrational number. What other famous irrational number do you know? Yes, it's an irrational number, just like pi, and it does come from somewhere. It's not random. So we have this number because we use it a lot. And for example, the number pi, 3.1415, blah blah blah, comes from, if you take any object that's circular, anything that's circular, and you divide by the diameter, you will get 3.14 roughly. That ratio of any circular object, from a small coin to the clock to anything, to a tire on a car, you take the circumference and you divide by the diameter, it's going to be about 3. That ratio always holds. So I want to kind of explain where this number e comes from. So it comes from, if you take this expression, and I want you to tell me where this looks familiar. You take this expression 1 plus 1 over n raised to the n power, okay? And if you put a really big number in for n, like a million, this will be 2.718, etc. It will be. So it would be fun for you to try that, actually. So the bigger the number you put in for n, it doesn't start out as 2.718. If you just put, for example, if you put 1 in, what do you get? Can you do that in your head? If you put 1 in for n, you get 2, right? So it's not 2.718 yet. But if you put really big numbers in, this is kind of the concept behind calculus limits. The limit of this as n goes to infinity is this number. And where have we used this? Does that remind you of anything at all that we've done so far? 1 plus 1 over n raised to the n? It actually looks like something you've seen recently. Yeah, Jake? Yeah, it's exponential growth, and in particular, when you do compounding interest, you know how you do the rate divided by the number of times you're compounding raised to the n power? So it's related to that. And actually, continuously compounding interest, there's a formula that uses the number e. But that's just a little bit of background. So all we're doing is we are just going to get a nice exponent review by simplifying expressions. So the main goal here is that you're aware of this constant e, and simplify the expression. You're aware of the constant e, kind of have a rough idea where it comes from, but moreover that you don't freak out when you see it. So, for example, if I have e to the 7th power times e to the 4th power, you don't need to, let's simplify that. What is that? We're just going to review the laws of exponents. It's e to the 11th. Yep. So you treat this constant just like you would a variable, actually. So you do the same thing. So let's try this. 2e to the negative 3 times 6e to the 5. What would that become, just using what you know already? You'd multiply the constants together. Yeah, Luca? 12e squared, exactly. So 2 times 6, 12. When you multiply, you add the exponents. So you're familiar with this. We're only going to do 2 more examples, and then you'll get to try it. So 24e to the 8th over 4e to the 5th. What is that? 6e to the 3rd, yes. And last one, so you would divide these and you would subtract the exponents. The last one, 10e to the negative 4x power. This you definitely can't type in on your calculator because it has a variable x in it. So you can't just type type that in your calculator. Let's simplify that using the laws of exponents. So first, you would cube everything inside the parentheses. So 10 cubed is 1,000, just 1,000. E to the, an exponent raised to a power, what's the rule? You multiply them, so you get negative 12x, and then we can't have negative exponents, so the 1,000 is fine. It's okay to have it, if you had negative 1,000, that's not a problem, you leave it alone. 1,000 is fine, but we're going to move this down, so it becomes e to the positive 12x, and that we can't simplify any further, so we just leave it like